Okay, let's unpack this. If you've been tracking the AI boom over the last couple of years, it feels like the whole conversation is dominated by one thing.
Large language models, LLMs.
Exactly. They can write poetry, summarize dense documents,
Yeah.
even generate code. I mean, their impact is undeniable. But as the hype kind of settles, there's this core question that keeps coming up.
A big one.
Is the engine that powers these massive systems, this idea of next token prediction,
Yeah.
is that really the path to artificial general intelligence?
And that really is the turning point we're at right now. Because while these LLMs show this incredible statistical fluency, the consensus is growing that the real path to AGI, it requires a fundamental shift.
A departure from just predicting the next word.
A total departure. We're seeing these critical, inherent limitations that, statistical fluency just can't solve on its own.
And we're not talking about small bugs here. These are like structural constraints in the architecture itself, right?
Absolutely. The LLM architecture fundamentally struggles with, well, four things we see as essential for general intelligence. Okay.
There's a deep logical fragility, constant factual hallucinations, a critical absence of physical grounding.
No connection to the real world.
Exactly. And finally, just staggeringly extreme energy and efficiency.
So our mission today is to go beyond the transformer. We're going to dive into five, well, pretty radical alternatives that leading labs are exploring.
The ideas that could actually bridge that reasoning gap.
Yeah, moving AI from a sophisticated pattern matcher to a genuine intelligent agent. We'll look at neurosymbolic systems, world models, active inference.
Plus neuromorphic computing for the energy side, and these structural blueprints called cognitive architectures.
Let's start with a reality check on the problem itself. The core training objective, next token prediction, or NTP, it's actually pretty simple mathematically.
Deceptively simple.
It's just trying to maximize the probability of predicting the next bit of text based on everything that came before it, maximizing the log likelihood.
And that's really where the trouble starts. This approach, it's great at capturing massive statistical nuances, which is why the models are so fluent.
Right. But it frequently causes them to settle into what we call a local minimum of reasoning abilities.
Meaning what, exactly?
Meaning the model learns to exploit these subtle surface-level correlations to get the answer right, instead of actually learning the underlying logic or rules of the task.
That sounds a lot like really, really sophisticated plagiarism, not, true understanding.
That's the most common critique, yeah. And you see this fragility really clearly when you try to force them into complex, multi-step logic.
Like asking for a weird format or something.
Exactly. Give the model an instruction that's just a little different from the norm. Say, you demand 1 indexing instead of the usual 0 indexing in programming.
Okay.
The model will often just default back to the common statistical pattern, completely ignoring the explicit rule you just gave it. It's matching the surface, not following the instruction.
And then you have the data problem. We feed them trillions of words, but they still have no common sense.
That passive data problem is colossal. Think about the scale of sensory data. A 4-year-old child processes an estimated 10 to the 15 bytes of visual, tactile, and auditory data
Per second.
through active interaction. An LLM might train on what, 10 to the 13 tokens of static text in its entire life?
That is a massive gap, a data bandwidth gap.
And that gap is precisely why LLMs struggle with embodied common sense. Knowing how much force to use to pick up a coffee mug or how to arrange dishes in a dishwasher.
So if the data type itself is flawed, does that mean we need to rethink training even within the current transformer sliction?
It does suggest some alternatives, at least for certain phases. One idea is something called critical token prediction, CTP.
Okay, what's that?
Instead of predicting every single token, CTP focuses the training on only the most essential ones for the task's logic.
That sounds more efficient.
It is, but there's a nuance. NTP is actually better during that huge initial pre-training phase. All that noise acts as a kind of regularizer. It forces robustness. But when you get to the specialized fine-tuning stage, SFT, CTP becomes the smarter strategy. It's faster and much more targeted toward locking in specific task logic.
So if pure statistics will always fall short, maybe the answer is bringing back, well, the rules. That takes us to neurosymbolic integration, or NISI.
The great unification.
Yeah, this is the idea of unifying the two cultures of AI connectionism, our neural nets, and symbolic logic, the old expert systems.
It's a really pragmatic hybrid approach. It's designed to get the best of both worlds.
How does it work?
NISI systems use the fast, intuitive, kind of guess-and-check pattern matching of neural networks.
What psychologists call System 1 thinking.
Exactly. And they combine that with the slow, deliberate, rules-based deductive reasoning of symbolic systems. That's your system 2.
And the big win here is tackling the black box problem, isn't it?
That's a huge part of it. The symbolic component gives you this transparent, interpretable scaffold for the reasoning. You can actually see the logical steps the machine took.
So it's not just a magic answer.
Right. Henry Cott's laid out a few ways they can interact, but the most intuitive is the neuropipe symbolic setup.
Neuropipe symbolic.
The neural net takes in messy, real-world input, like a blurry photo or a complicated sentence, and it converts it into clean, abstract symbols. Then it just hands those symbols over to the symbolic engine to manipulate with hard logic.
Can you give us a concrete example of where this has been a real breakthrough?
Oh, absolutely. Look at DeepMind's alpha geometry. It's incredible. This system solves complex Olympiad-level geometry problems.
Which are notoriously difficult.
And it shows that perfect System 1, System 2 split. The neural model acts on intuition. It proposes novel geometric constructs, like drawing a clever auxiliary line that wasn't there before.
The creative leap.
That's the one. Then, once that intuitive guess is on the table, the symbolic deduction engine takes over to rigorously, formally prove the result with traceable logic.
So the intuition is needed to unlock the problem, but the logic is needed to validate it. But wait, if we bring back a symbolic part, aren't we just reintroducing the brittleness problem that LLMs were supposed to fix?
That is a very fair and critical question.
Symbolic systems were famous for that. One broken rule, and the whole thing just collapsed.
The difference now is how they're used. The neural component handles the fuzziness of the real world, the perception part. The symbolic component only ever operates in that clean, abstract reasoning space.
Okay, so they play to their strengths.
And that synergy makes them way more robust. Plus, in high-risk domains medicine, autonomous robotics, you have to have interpretability. You need that error handling.
You need to know why it made a decision.
A symbolic constraint can tell a robot, you cannot grasp this object with more than X force. Or, tell a medical system, this diagnosis violates condition Y. Amazon's Vulcan robots use logic like this to enforce safety constraints in their factories.
Okay, so Nessie tackles the logic problem. What about the physics problem? This brings us to Jan LeCun's big vision of world models. He argues that if LLMs are flawed because they predict the next word, then generative video models are also flawed because they're trying to predict every single pixel.
That's his core philosophical break. He says that generative architectures trying to predict, say, the next few frames of a video run into an infinite list of possibilities.
What does he mean by that?
Well, think of a ball rolling off a table. The system has to predict its trajectory, sure, but also the exact shadow, every reflection of light, tiny air currents.
All the stuff that doesn't actually matter for the outcome.
Exactly. It's computationally crippling, and for intelligence, it's completely unnecessary.
A human just cares that the ball is going to hit the floor. We don't simulate the exact light refraction in our heads. So how does a world model filter out all that noise?
The solution is the Joint Embedding Predictive Architecture, or JEPA. It uses self-supervised learning to predict missing parts of a video, but, and this is the crucial part, it does so in a compressed, latent embedding space.
Not in pixel space.
Not in pixel space. This allows it to learn to ignore all that irrelevant, high-frequency noise, like a flickering light bulb or TV static, and focus only on the semantic, the conceptual features that are critical for planning.
So the world model isn't trying to generate a photorealistic video, it's generating a conceptual blueprint, a simulation engine for what happens next.
Precisely. The ultimate AGI vision here is highly modular. You'd have 4 parts. A perception module to create that compressed representation.
Okay.
The world model itself, which is a simulation engine. Then a cost or objective module that sets goals and guardrails.
And the last piece.
And finally, an actor or planner module that uses the simulation to reason. And in this framework, reasoning isn't a search problem, it's an optimization problem, finding the action sequence that minimizes the predicted cost.
And we've already seen VJPA V2 planning robotic movements like grasping things or opening doors just by anticipating outcomes in that conceptual space.
Yes, that's the simulation engine at work. And that brings us to the next logical step. If the world model is the simulation engine, how do we give that engine its own goals, its own intrinsic motivation?
And this is where things get really interesting because the concept comes straight from theoretical neuroscience. We're talking about active inference.
Which is all rooted in the free energy principle, or FEP.
Okay, so the free energy principle, it's a pretty dense mathematical framework. Can you simplify it for us?
I'll try. The FEP basically posits that any self-organizing system, from a single cell all the way up to a human, has to maintain its internal state, its homeostasis, by minimizing something called variational free energy.
And variational free energy, or VFE, is what?
Think of it as a manageable stand-in for surprise. If your internal model of the world is constantly being surprised by reality, your model is bad. To survive, an agent must minimize that surprise.
So a thermostat minimizes surprise by keeping the temperature stable.
And a predator minimizes surprise by making sure its prey doesn't escape its model of where it should be. The key is that the agent actively tests hypotheses about the world to confirm its model, instead of just passively taking in data.
So the intelligence isn't just learning from data, it's acting specifically to test and refine its own assumptions about reality.
Correct. And when you apply FEP to planning, the old boundaries between perception, learning, and action just collapse. Planning becomes an inference process. The agent selects actions that it predicts will minimize expected free energy, or EFE.
What are the levers there? What drives the agent to actually act?
There are two fundamental values driving that EFE minimization. The first is epistemic value.
Epistemic meaning knowledge.
Right. This drives actions that resolve uncertainty and maximize information gain. It's the pure curiosity drive. The self-motivated scientist impulse
And the second value.
is extrinsic value. This drives actions that align with the agent's built-in preferences or goals. Its desire to maintain a predictable, preferred state.
So an agent's actions are always a balance between learning new stuff and achieving known goals. That sounds remarkably human.
It is. And while this is all highly theoretical, toolkits are starting to emerge. Libraries like arcsinfer.jl and Julia can actually implement this for real-time Bayesian inference. They are tracking hidden states and systems up to 300 times faster than older sampling methods, so it's moving from pure theory towards practice.
We've covered logic, physics, and motivation. But now we have to talk about the physical structure and the, staggering cost of running these current models.
Yeah, the energy consumption of LLMs is colossal.
It is not sustainable for wide deployment.
Not long-term, no. We need a fundamental change in the hardware, which brings us to spiking neural networks, or SNNs.
SNNs, often called the third generation of neural nets. How are they different?
Well, standard neural nets, ANNs, are continuously active. They're always burning energy. SNNs are inspired directly by the brain's efficiency. They're event-driven. Neurons only communicate using these discrete spikes in response to specific stimuli. This sparse activity just drastically cuts down on power consumption.
Can we apply that kind of brain-like efficiency to the most power-hungry part of the current architecture, the self-attention mechanism?
We can, and researchers have. It's called spike-driven self-attention, or SDSA. Standard self-attention relies on these massive, power-intensive, multiply and accumulate operations, MCs.
Okay.
SDSA replaces them with sparse addition operations. And by moving from continuous multiplication to discrete, event-driven addition, they've shown up to an 87.2 times reduction in computation energy.
87 times. That's a real-world consequence. This isn't just about saving money in a data center.
No, it's about making AGI feasible to run locally, on a tiny drone, a robotic arm, or a medical implant, completely untethered from the cloud.
And on a similar note, I've seen things about liquid neural networks, LNNs.
Right, another efficiency play. They use differential equations to model system dynamics, which lets them adjust their own weights and connections online in real time.
Unlike the frozen static weights of a big transformer.
Exactly. LNNs are incredibly noise-resistant, and they adapt on the fly, which makes them perfect for dynamic edge deployments.
Okay, that handles the hardware and efficiency side.
Yeah.
Let's pivot to structural models that are less about biology and more about simulating human thought processes. What about cognitive architectures?
Cognitive architectures, systems like SR and ACTR, are essentially blueprints. They try to simulate the interacting functional modules of the human mind.
Like what?
Things like working memory for short-term focus, procedural memory for skills and rules, and declarative memory for facts. They generalize not just from statistical patterns, but through explicit, predefined rules.
And what's the cutting edge there? How do you make those architectures flexible enough to compete with modern neural nets?
The frontier is really about unifying all those different types of knowledge. You have projects like OpenCog Hyperon, which uses a unique language called Meta. It stands for Meta Type Talk. It lets the system integrate logical, functional, and probabilistic programming all onto a shared knowledge base, a metagraph they call the distributed atom space.
So it's one unified structure for everything.
That's the idea, to have one place where all these different AI tools, reasoners, planners, learners can all interact and collaborate, pushing towards true human-level generalization.
All these really sophisticated ideas, logic, simulation, active learning, they all bring us back to one huge hurdle, the messy reality of the physical world,
Yeah.
which is why we're seeing labs, even OpenAI, pivot back to robotics. They're arguing for embodied intelligence.
The simple fact is that common sense requires a physical carrier. The world is built for bipedal movement and for hands that can manipulate things.
And that's the data collection hypothesis.
Exactly. Humanoid robots, whether it's Tesla's Optimus or UBTech's Walker S2, they are the optimal sensors for gathering that diverse sensory motor data. The feel, the physics, the interaction, all the stuff that passive text can never capture.
So embodiment solves the input problem, getting the right kind of data. What solves the output problem? How do we prove that an AGI candidate is actually better than an LLM at genuine fluid reasoning?
We need benchmarks that can't be gamed by just matching patterns. And right now, the definitive test for fluid intelligence is the ARC AGI-2 benchmark.
I've heard of this. It's like an IQ test for AI.
Pretty much. It presents these abstract grid transformation tasks where the agent has to figure out a new abstract rule from only 2 to 5 examples. It's famously easy for humans, but incredibly hard for AI.
And how do our best, most powerful LLMs, the ones that ace every other academic test, how do they do on this?
They often score a shocking 0%.
Zero.
Even the frontier models, like GPT 4.5, fail to generalize the abstract rule because they lack the necessary algorithmic structure.
What are they missing?
They're missing refinement loops, algorithms that can do iterative internal thinking time to transform and verify an answer. That inability to internally think and refine is the core reasoning gap left by pure autoregressive models.
That zero score is powerful proof that just making the models bigger isn't the answer.
It absolutely proves that AGI needs smarter algorithms, not just more parameters. I mean, we've seen tiny recursive models, TRMs, with only 7 million parameters, a tiny fraction of any LLM, achieve actual success on this benchmark by focusing their small resources on those recursive refinement loops. The lesson is clear: algorithm over scale.
So what does this all mean? If we synthesize these 5 alternative paths, the neurosymbolic logic, the world models, active inference, efficient SNNs, the cognitive architectures, the consensus seems clear. AGI won't be one single algorithm.
That synthesis is the key. It points toward a highly integrated hybrid architecture. You could call it a two-headed monster.
A two-headed monster.
Yeah. You need world models for the grounded physical understanding. You need active inference for the autonomous agency and curiosity. And you need neurosymbolic logic for the rigorous, reliable reasoning.
The goal is moving beyond what LeCun calls probabilistic parrots.
Exactly. Moving toward truly autonomous, reliable agents that can actually interact with reality in a complex way.
And if we look out toward that horizon, what's the ultimate frontier? The thing that separates a truly general intelligence from just, a highly advanced machine intelligence.
That frontier is metacognition.
Okay.
The ability of an AI system to self-monitor, to adjust its own cognitive processes. It has to have an internal mechanism to know, when do I rely on my fast, intuitive system 1, guess, and when do I need to stop, slow down, and trigger a rigorous rules-based system 2 search? The whole shift is about prioritizing adaptability and reliability over just statistical fluency.
A system that knows what it doesn't know.
Precisely. And if we accept, as active inference suggests, that planning is really an inference process that maximizes both learning and its own goals, well, that raises a profound final thought for you to consider.
Let's hear it.
If an AGI is designed to be an autonomous scientist, driven by its own curiosity, what fundamental prior preferences must we hard-code into its core to ensure that its inherent pursuit of information aligns perfectly with the fundamental safety and stability of humanity?